in this lesson and the next lesson we're going to look at the half-life of radioactive materials. To do that, we're going to take a sample of a radioactive isotope. Now, if you'll permit me, this is just an imaginary sample, and I'm going to use this to construct a pictogram to try and help you see what happens during radioactive decay. Now, the first thing we should say is that it's impossible to say exactly when a radioactive isotope will decay from this sample, or which radioactive isotope will decay. These things are completely indeterminate. We cannot say which or when, but what we can say is that within a certain period of time, a certain fraction of these radioactive isotopes will have decayed. Now, the term that we use to describe this is called the half-life. And we can say this, that within the half-life of the radioactive sample, exactly half of the radioactive isotopes now present will decay. Okay, let's just summarize that. So we can say that the half-life, which is given the symbol T, okay, big T, is the time taken for exactly half of the radioactive isotopes present in a sample to decay. Right, so let's just assume that we're starting at time t equals 0, okay, and that at that moment none of these radioactive isotopes have decayed. So if we advance then by a time t, that's to say by one half-life, then we'll find that half of those radioactive isotopes will have decayed. In the next half-life period, half of these radioactive isotopes, which are now present, that's the grey atoms, half of these will decay. Okay, so these are now the radioactive isotopes that are present, and now we can say that in the next half-life period, exactly half of these will decay, and so on and so on. So we started off with n radioactive isotopes. After one half-life, we then had n by 2 remaining. After another half-life, we have half of those, which is n by 4. After another half-life, we have half of those, which is 1/8 of the number that we started with. Okay, so if we plot these results on a graph, okay, so we'll have time along this axis, and going up this axis we have the number of radioactive isotopes remaining. I'll put radioactive isotopes there remaining. Okay, so we started off with n radioactive isotopes. After one half-life period, that number had dropped down to here. We're at n by 2, and then another half-life period, we're down to here, which is n by 4, and another half-life period, we're down to here, which will be n by 8. Okay, and then n by 16, and then n by 32, and so on and so on. So again, repeating, after each half-life period, the number of radioactive isotopes remaining drops by 2. Now, this type of curve is known as an exponential curve, and an exponential curve always drops or rises, depending on which way it goes, by the same fraction or proportion in the same period of time. So this is an exponential curve because the number of radioactive isotopes present drops by the same fraction, that's to say 1/2, in the same period of time, t, which is the half-life. One thing I'd like to point out here is that it's actually very hard to measure the number of remaining radioactive particles there are in the sample at any one moment. This isn't really a practical way of going about measuring radioactive decay. A much more practical way is to measure what we call the radioactive decay rate, or the count rate, and we'll look at that in the following lesson.